Welcome back to Applied Algebra and Trigonometry. We're going to continue talking about trigonometric identities. You will find a list of trigonometric identities posted on Blackboard in the Contents section of our course. I suggest you pause the video and download that before you continue. I have posted the mnemonic device that I talked about in the previous video, but you really need to have that other sheet of paper in front of you. First, let's talk about multiplying, which may involve some distributing, and then simplifying the result. Here's our first example. Notice that I've moved away from using theta. I'm now using x to indicate the angle, but that's fine. You can do it either way. You can use whatever variable you want to, as long as it clearly communicates to your audience that that is an angle. All right, so we're going to distribute this just as we would with any number, any variable. That gives us the cosecant of x times the sine of x. And just like if we had the variables x and y, we would not have to put a multiplication sign around them. It would be assumed that it is multiplication. If you see two trigonometric ratios written one after the other, it does mean multiplication. All right, so cosecant of x times sine of x, then we distribute it further, and we get the cosecant of x times 3 times cosine x. All right, looks like we didn't simplify it any, but let's work on that simplification now. Because if you remember, cosecant is the reciprocal of sine, so we can rewrite cosecant of x as 1 over sine x, and we're still multiplying that by sine x. And we can put any number over 1, or put a denominator of 1 and under any number, including the number sine of x. And then we have 1 over the sine of x times 3 times the cosine of x. And that's all going to be over 1. But when we multiply 1 over sine x times sine x, we just get 1. And then over here we have 3 times the cosine of x over sine x. But we also know that the cosine of x over sine x is equivalent to the cotangent of x. So that's a much simpler way to write what we started with, or what we originally got after we distributed. So we have done our multiplication, and we have simplified it. Okay, and now we are going to multiply this. You can think of this as distributing, but if you look closely, look at these factors of the product you are about to form, and you will see that this will actually be sine squared of theta minus 1. This is a difference between two squares, which factors as you see it above. So you can either work it out, add it up, you'll be fine, or just recognize it for what it is. All right, but sine squared theta minus 1. Does that look like anything we've seen before? Well, how about this? We do have sine squared in a relationship with cosine squared, oops, better put my theta in there, equals 1. So if we subtract 1 from both sides, we're going to get this equals 0. Then if we subtract cosine squared from each side, look at what we have. We have the sine squared theta minus 1 left on the left-hand side, which is what we had after we did the multiplication in our example. What is sine squared minus 1 equal to? Well, what remains on the right side of that equation? Negative cosine squared of theta. So that is our final answer here. Negative cosine squared of theta. Here's example 3. The cosine squared of alpha times the quantity 1 plus tangent squared of alpha. So we are going to distribute just as we have before. So cosine squared of alpha times 1 is itself, plus cosine squared alpha tangent squared alpha. That looks a little bit interesting. All right, so what is cosine squared of alpha times tangent squared of alpha? And by either looking at my sheet of trigonometric identities or looking at this hexagon over here or just remembering it, I can tell you that tangent squared of alpha is the same thing as sine squared of alpha over the cosine squared of alpha. And that's simply because tangent of alpha itself equals sine of alpha over cosine of alpha. Now I'm multiplying that by cosine squared of alpha, and I can put that over 1 since I'm going to be using it, or I'm going to be multiplying by a fraction. And I am still going to remember that I have to add cosine squared of alpha. All right, when I go to multiply those, I get some cancellation there. And so I have sine squared alpha plus cosine squared alpha, which should look very familiar. In fact, it equals 1. It is listed on your trigonometric identity sheet, and it is also listed up here on your hexagon. Only it's in reverse on your hexagon and probably is on your identity sheet also. That's enough multiplication. Let's divide or factor and simplify. Example 4. Sine theta minus sine theta times cosine squared theta. Separated by a subtraction sign. Is there any common factor in those two terms? Yes. There is a common factor of the sine of theta. Sine theta goes into the first term 1 time, and it goes into the second term cosine squared of theta times. You can check it out. See if you were to distribute sine of theta to both terms within the parentheses, you would find that you get back where you started, which is not the direction we want to go in. So let's keep going. 1 minus cosine squared of theta. Where do I see a cosine squared? Well, let's see. Sine squared theta plus cosine squared of theta equals 1. So if I subtract cosine squared theta from both sides, I'm going to get sine squared theta equals 1 minus cosine squared theta. Okay. So this is equal to sine squared theta. I still need to multiply it by sine of theta, though. So I'm going to get sine cubed of theta. And we're done. Let's do another. For our next example, we have tangent squared of t times secant squared of t minus tangent to the fourth of t. Well, I see tangents in each of the two terms that are there. But a little complicated. We're getting up into the fourth power of tangent. So remember, at any time when you see something that looks a little more complicated than you're comfortable with at the moment, you can always make a substitution. Maybe you want to let b equal the tangent of, what's the highest power here of t that's in each term? Well, that would be tangent squared of t. So I could write b times secant squared of t minus b, but that's only tangent squared of t, right? So it has to be b squared. It has to be tangent squared squared. So now when you look at it, you can see that b is the greatest common factor, and we have left secant squared of t in the first term, and we have b left in the second term. Now that's as far as we can go with the b and manipulating it to make things simpler. So now it's time to put our tangent squared of t back in everywhere we see a b. So we have secant squared of t minus tangent squared of t. Is there some place we can go from there? Secant and tangent. Which identity do you see that combines both of those? Well, if you're looking at the hexagon over here, tangent and secant are combined in this triangle. And that triangle there indicates that the tangent squared of theta plus 1 equals secant squared of theta. So that means that if you subtract tangent squared from both sides, tangent squared of theta, subtracting it from both sides, then you will be left with 1 on the left-hand side equals secant squared of theta minus tangent squared of theta. Notice how I went and moved back to theta from t. Let's keep that the same. Okay, so that tells me that everything within the parentheses is actually only equal to 1. And I'm multiplying that by the tangent squared of t, which is simply itself. One last example of factoring and simplifying. Okay, the common factor in each of those terms is the sine of u. So that gives us 1 plus the cotangent squared of u. All right, and 1 plus cotangent squared of u. We've moved over to this triangle here, which tells us that 1 squared, which is 1, times the cotangent of u. Let me be consistent this time, but it's just not just cotangent u, it's cotangent squared of u. So remember, we have these little squares to remind us. Okay, 1 plus cotangent squared of u equals cosecant squared of u. So we actually have cosecant squared of u here, and that is multiplied by the sine of u. Are we done? Well, no. Okay, cosecant is the same thing as 1 over sine. So instead of cosecant squared of u, we have 1 over sine squared of u. Let's multiply fractions by putting sine u over 1. And now we can cancel because sine u goes into here once, and it goes into here, well, sine u times. So our final answer, we have 1 over the sine of u. Let's simplify further. The reciprocal of the sine of u is the cosecant of u. Now we are finished with this example. So we have multiplied and simplified, we have factored or divided and simplified. So now let's talk about proving trig identities. And actually, I'm going to move this down here and write out or type out the steps to doing that, and then we'll have some examples over on the right. The word steps might be a little strong. These are more like suggestions. Number 1, try to identify what might happen before you change things. Number 2, try to work with only one side of the equation. Number 3, try to recognize patterns. Okay, I'll be a little more forceful. Avoid errors. And oops, there's an error. So here's example 7 and the first example of proving trigonometric identities. Okay, there's an identity. This is saying the stuff on the left can be identified as the stuff on the right, or cosecant of theta over secant of theta equals the cotangent of theta. Can we prove this is true? Well, let's see. Cosecant of theta, we can look over here on our hexagon, or we can look at your sheet, or you may just remember that cosecant is equal to 1 over the sine of theta. So this becomes 1 over the sine of theta, and secant is the reciprocal of cosine, so that becomes 1 over cosine theta in the denominator, and that's equal to cotangent of theta. All right, now I have a complex fraction. So let me do that division that's indicated there. 1 over sine theta divided by, well, but I'm working with fractions, right? So when I divide fractions, I actually multiply by the reciprocal. So that's cosine theta over 1, and that's going to equal cotangent. Notice I'm not touching the right-hand side. I'm only dealing with the left-hand side. When I do that multiplication, I get the cosine of theta over 1. Nope, I get the cosine of theta over sine of theta. And that still equals the cotangent of theta. And cosine of theta over sine of theta is truly equal to the cotangent of theta. That is one of the basic identities on the identity sheet that is in the content section of Blackboard. We have just proved that the identity with which we started is true. Example 8 shows you why you should think a little bit before you just jump right in and try to do something. So I'm looking at this identity. I have a ratio on the left and a ratio on the right. I'm looking around my hexagon here. I'm looking through my identities. I don't see anything with just 1 plus cosine of theta or just 1 minus cosine of theta. I see things with cosine squared of theta and 1. And I see some sine squared things. So let's look at this a different way. I have a ratio equals a ratio. I have a proportion. How do you solve proportions? Well, you cross multiply. So I'm going to cross multiply. And look, when I look at this, I'm going to be writing here 1 plus the cosine of x times 1 minus the cosine of x. And when I do the other part of the cross multiplication, I'm going to get sine squared of x. Now that's starting to look like things from my identity sheet, especially after I do this distribution, because it's going to give me the difference between two squares. You can go ahead and do the distribution yourself and see that the middle terms add to be 0. All right, 1 minus cosine squared of x equals sine squared x. Well, where do I have cosine squared and sine squared? Right here. I have a square of the sine and a square of the cosine, and I have 1 in this triangle. That's sine squared of theta, or x in this case, plus cosine squared of x equals 1. So if I subtract cosine squared of x from both sides, I'll get the sine squared of x equals 1 minus cosine squared of x. Okay, this is what I have on the left-hand side. I'm going to substitute this for what I have on the left-hand side, and that gives me sine squared of x equals sine squared of x. Done. We have proved the original identity. All right, one more. Example 9 will be the last one. This one is going to be rather challenging. You may want to go to your homework do some examples, some simpler examples, become familiar with this, and then come back to see how to do a more difficult identity, how to prove a more difficult identity. The cosecant of b is my angle for this one, over the cosine of b minus tangent of b equals the cotangent of b. Well, I have a fraction there. I suppose I could add tangent of b to both sides, but then I would be changing both sides. Let's see if we can only work with one side. And I would really like to simplify this mess. So I have a fraction. I can add things to fractions if I can find a common denominator. So let's do that. So I have tangent b in my equation, in my identity, but I want tangent b to be over the cosine of b. I need to find a common denominator. Well, I have to multiply 1 by the cosine of b to get cosine of b. So I'm going to multiply tan b by cosine b. And what do I get? I get tan b cosine b. That's it. Okay, that's looking a little bit complicated, but we can handle it. Okay, that's going to give me the cosecant of b over cosine of b, and then I still have this negative. I did not carry it down to work with below, so I'm going to put the negative in there, and then I'm going to bring up what I found, which is tangent of b times the cosine of b. And by the way, are there other ways to do this? Absolutely. This is another situation. When you are proving trig identities, there will be multiple ways that you can work with them, multiple steps you can go through, but at the end, both sides of the equal sign will read the same thing. Be careful when you're working with these. I'll tell you a little secret. I have had to erase and rewrite this part of the fraction a couple of times because I so want to pull a cosine b out of this that I keep miswriting cosecant of b as cosine of b. So be very careful you do not make that mistake. Notice that I changed the color of tan b, and that's because I'm going to rewrite the tangent of b as the sine, there I almost wrote cosine again, sine of b over, now I can write cosine of b. That's what the tangent of b is equal to. Okay? But now I'm multiplying that by the cosine of b. Watch what happens if I put cosine of b over 1. Now I can cancel. And what does that give me? Oh, well, look at this. I can take that cosecant of b that I keep trying to rewrite and rewrite it, not as cosine, but as 1 over sine b. What do I have left now? Wow, it would be great if 1 over sine b were multiplied by sine b, because then it would cancel and we just have 1. But no, we have a subtraction. And when we have a subtraction, we have to find a common denominator to work through it. What do I have to multiply 1 by to get sine b? Well, I have to multiply by sine b. So if I do it in the denominator, I must do it in the numerator. So we get sine squared b over b. Over here, that looks like 1 minus sine squared of b over sine of b equals cotangent b. Okay, and that's, wait, one more thing. On the left-hand side, we still have the cosine of b. What are we going to do with this? Well, first we're going to move it all up so we have a little more room. Make it a little bit smaller there. Okay, so 1 minus the sine squared of b is actually equal to cosine squared of b. This should start becoming a little more familiar to you. And that's still over the sine of b, but the whole thing is divided by the cosine of b. It still has to equal the cotangent of b. All right, we have a complex fraction. Let's take that numerator. Cosine squared b over sine b is the numerator here. And we're going to divide by the denominator. Wait a minute, we're dividing into a fraction. So let's work with the reciprocal. Let's multiply by the reciprocal of cosine b. Well, that's 1 over cosine b. Cosine b divided by cosine b is equal to 1. Cosine squared b divided by cosine b is equal to cosine b. But everything on the left is still equal to cotangent of b. Well, what is cosine b, which is what we have left here, over sine b? Cosine b over sine b? Well, that's just the cotangent of b. You may take one more step before doing that. I just didn't want to move everything up again, and I was trying to keep things a little neater here. Okay? But we have proved the identity. At the end, we have cotangent of b equals cotangent of b. So that proves that this original identity works. It is true. Well, that's all I have for you on proving trig identities until we meet in our Collaborate session. So I will see you then.